I'm Mark Kavanaugh for Kavi Coaches, and today I'm going to coach you up on working through a couple of examples of drawing energy bar charts and writing conservation of energy equations. In this video, we're going to talk about energy bar charts and draw a couple of examples and how that relates to conservation of energy. So here's an example. So we have a marker that's dropped to the floor. The initial situation being the marker at the top, and the final situation is how fast it's moving when it hits the floor. So it's the moment it hits the floor. So step one is to define the system. So we have the marker, which is moving, and the earth. There's no spring. We could use my hand and put it outside the system, but the marker is already at the top. If the marker wasn't at the top, then my hand would be providing work. So now let's ask the three questions. Is anything moving? No. Is there a spring? No. Is there anything that has a height greater than 0? Well, yes, the marker. So then we have the gravitational potential energy in the initial situation. Now the earth transfers the energy to the marker, giving it kinetic energy. So we're going to talk about the three questions again. Kinetic energy, yes, there's no spring, there's no height at the final. So since the arrows stay inside the system, that means the initial height has to equal the final height, total height of 4 in both situations. Then we write our conservation of energy equation. And then we're going to cancel out the mechanical energies we did not use. So we didn't use the kinetic or spring energy in the initial, or spring energy or gravitational in the final. Now we have to ask ourselves about work. Well, we look and we can see that all the arrows stayed inside the system. We only had one, so that means work is 0. That simplifies our equation down to initial gravitational energy equals the final kinetic energy for this example. Now let's look at a different example. So this one, we have a spring stretched horizontally from equilibrium to 1 meter, like we did in the Hooke's Law lab. So we start with our system, and our system is defined as the spring and the earth. Well, since the spring doesn't really change height, we could omit the earth. I like to put the earth in the system each time so I don't forget it. So we ask ourselves this three questions. Is there a spring stretched or compressed? Well, it's before the spring stretched, so no. Nothing has a height greater than 0, nothing's moving, so I don't have any energy in the initial situation, which means there has to be something outside the system that is providing the energy to the spring. And what is that? Well, that's my hand. My hand is pulling the spring. So my energy flow shows the hand giving the spring energy. Then I ask the same three questions again. Is there anything moving? No. Height greater than 0? No. Spring stretched or compressed? Yes. So the spring is stretched 1 meter, so we have stored spring energy. So writing the conservation equation, we start with the long equation with all the mechanical energies in work. And we know there's no mechanical energy in the beginning, only stored spring energy in the final, which means that there's going to be work. Now the hand is transferring energy into the system, which means that's going to be a positive value of work, so plus work. And I like to put a subscript on work to show what object is applying that work. So the work done by the hand is equal to the stored energy in the spring in the final situation. So let's look at a third situation. So we have a car rolling up a hill and it has friction and it slows to a stop. So again, we're going to define our system. We have the car and the earth, so there's no spring, so we don't have to worry about asking that question. The car is rolling, so that means there's kinetic energy. We can define the lowest point in the problem, which is the moment the car rolls up the hill, as 0, so there's no gravitational energy. So where does the car's energy go? In the flow diagram, we know that the car is going to slow down, so the car is losing energy to the earth. But we also have to take into account friction. So the frictional force is provided by the hill, and the car is losing energy to the hill as well. So we're going to draw an arrow from the car to the hill. Now this tells us that the initial energy has to be greater than the final amount of energy. So when we ask those same three questions, is anything moving? No. Is there spring? No. But something has a height greater than 0? That means because energy was lost to friction, the final amount of energy has to be less. It could have been 3, could have been 2, could have been 1. I just chose 2. It doesn't really matter. All that matters is that the energy in the final is less than the beginning because there's an arrow going out. Now we write our conservation equation. We're going to cross out any mechanical energies that we don't use in the bar chart. So no stored spring or gravitational in the beginning, no kinetic or spring energy in the final. And we do have work. There is work done by friction in this situation. And work done by friction has an arrow going out. So that's going to be minus W in this case. That's why we have plus or minus, because it depends on the arrow flow if it goes from outside in or inside out. And I put a subscript of F with work for work done by friction. So that's my third equation. So let's look at a fourth and final example for this video. So we have a car is compressed up against a spring, a lab cart, and it's launched up a hill and is moving at the top of the hill. So we define our system. So we have a spring, we have something that's moving, a car, and we have the earth. So we ask ourselves the three questions. Is anything stretched or compressed? Yes. The spring is compressed. So we draw US and draw a bar underneath that. The spring transfers its energy to the car, but the car also changes height throughout this. So that means the car is not going to be moving as fast if it was moving horizontally. So it loses energy to the earth, which means in the final situation, because it's still moving at the top, that means I'm going to have kinetic energy. I'm also going to have gravitational energy because its height is greater than 0. So I have kinetic and gravitational in the final. Now here's where the heights matter, because I drew a total height of 4 for spring energy, which means the total height for kinetic and gravitational combined has to be a total height of 4. So I can split it up however I want because it's a qualitative representation. In this, I chose to go 3 kinetic and 1 gravitational. It could have been 2 and 2. It could have been 1 and 3. It could have been 2.5 and 1.5, as long as it adds up to the total amount we had to begin with. The point of drawing the bar charts is to get to the conservation equation. So we write our long conservation equation, all the mechanical energies plus or minus work equals all the mechanical energies in the final. And we're going to cross out the kinetic energy and gravitational in the initial, and only the stored spring energy in the final situation. Then we ask ourselves about work. Are there any arrows going from outside in or inside out? The answer is no. So we're going to cross out work as well. So there is no work in this situation. So that simplifies our equation down to the stored spring energy initially equals the final kinetic plus the final gravitational energy. So these were 4 examples of how to use bar charts to write a law of conservation of energy equation. I hope this was helpful. I hope you have a great day and an even better tomorrow.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.